Hello everyone, my name is Hamza Zakia and today I will present our project titled Enhancing Brain-Computer Interface Communication Using Large Language Models. This project was prepared by Digital Minds Research Group for the course Large Language Models and Introduction to Brain-Computer Interface. Our group members are Musa Qabna, Hamza Zakia, Barak Qasim, Mariam Hussein, and Salam Tumaizi. Our course advisor is Faiza Rouhani. We wish her the best regards again. The main focus of this presentation is how large language models can improve brain-computer interface communication, especially when the decoded text from brain signals contains errors. So let's start with the first slide, the challenge, BCI communication. So brain-computer interfaces or BCIs are especially important for people who cannot communicate using normal speech or movement. For example, people with ALS, called locked-in syndrome, or severe paralysis may lose the ability to speak, type, or even move their body. So for these users, a BCI can become a direct communication channel between the brain and external devices. However, the core challenge is that EEG signals are not clean. They are noisy, weak, and difficult to interpret. Because of this, current BCI systems may achieve around 70 to 80% accuracy per trial. But in real-world communication, the error rate can still be very high. This means that around 25 to 40% of words may be corrupted. So even if the system works technically, the final message may still be hard to understand. For a user who depends on the system to say something important, even a small mistake can change the meaning completely. Let's go for the next slide. How brain-computer interfaces work. So now let's look at how basic BCI communication pipeline works. First, the user imagines a movement. This is called motor imagery. For example, the user may imagine moving their left hand or right hand. Second, EEG electrodes placed on the scalp detect neural activity patterns related to that imagined movement. So if I imagine moving my left hand, the EEG electrodes are gonna signal the neural activity in my brain. Third, signal processing techniques are used to extract useful features from the noisy brain signals. Finally, a classifier maps those brain patterns into text or commands. The problem is that the final decoded text is often grammatically broken or contains wrong words. So the BCI may understand part of the user's intention, but the output is not always accurate enough for natural communication. This is exactly where language models can help. So in slide 4, understanding the BCI decoding errors. BCI decoding errors usually appear in three main forms. The first type is substitution errors, which are the most common. This means one word is replaced by another word. For example, I need water may become I need wafer. This sentence is close, but the meaning becomes wrong. The second type is deletion errors. Happens when a word is missing. For example, I need water may become I water. Here, the message is incomplete, as you can see. The third type is insertion errors. This happens when the system adds an extra word. For example, I need water may become I need water pen. These errors are dangerous because BCI communication is often used for essential needs. A wrong word can make the user intentions unclear or even misleading. So the goal is not only to decode brain signals, but also to recover the intended messages as accurately as possible. Let's go to slide 5. Why large language models are the solution? Language models are useful here because of natural language has a lot of redundancy. In normal communication, every word is constrained by the words around it. For example, if someone says, I need some water too, the next word is probably something like drink, not a random word. Large language models understand grammar and syntax and meaning. They can recognize when a word does not fit the context. They can also infer missing or corrupted words. This makes LLMs powerful tools for correcting BCI output. They do not need to directly read brain signals. Instead, they work after the BCI decoder and clean the decoded text. So the LLM becomes a correction layer that improves communication quality by using linguistic context. Let's go to slide 6. Proposed system architecture. So our proposed system uses a three-stage pipeline. The first stage is EEG, signal acquisition and pre-processing. In this stage, the brain signals are collected and cleaned. The second stage is neural decoding with confidence scores. The system decodes the signals into text, but it also identified which words are sentient are uncertain. And the third stage is LLM correction with context. The language model receives the noisy decoded text, the confidence information as well, and the conversation history. And then it's just a corrected version of the message. The key advantage of this architecture is that it can work with existing BCI hardware. We do not need to redesign the entire BCI system. We are adding an intelligent correction layer on top of it, and this makes the approach modular and practical. So in slide 7, EEG signal acquisition. In the first stage, EEG signals are collected using a headset with around 16 to 64 channels. This sampling rate is around 250 hertz, which means the system records brain activity many times per 1 second. After collecting the raw signals, pre-processing is needed because EEG is very noisy. A bandpass filter from 0.5 to 40 hertz is used to remove unwanted frequencies such as slow drift and muscle noisy. A notch filter is at 50 hertz is used to remove power line interferences. Then independent component analysis or ICA can be used to remove artifacts such as eye blinks, heartbeat signals, and other noise sources. Finally, the signal is divided into short segments, usually around 2 seconds epochs, which are timed locked to users' codes. This pre-processing step is important because if the input signal is poor, the decoder output will also be poor. Slide 8, stage 2, neural decoding and classification. So in the second stage, the system tries to classify the clean brain signals. One technique is used here is common spatial patterns or CSP. CSP. It helps extract features that are useful for distinguishing between different brain activity patterns. than a classifier such as linear discriminant analysis or LDA maps those features into classes or commands. The output is decoded text, but also confidence scores for each token. This is important because the system can tell the LLM which words are likely to be wrong. For example, the raw decoded output may be I weed some water. This sentence is clearly wrong, as we mentioned, but it is close enough to the intended meaning. The word weed and the other word water may have low confidence, so the LLM knows where to focus. Instead of blindly rewriting everything, the LLM can make targeted corrections. LLM based correction. The third stage is the LLM correction stage. Three components of the prompt. The third stage is the LLM correction stage, as we mentioned. The prompt is given to the LLM contains three important components. First, there is a system instruction explaining that the input comes from a BCI communication system and may also contain decoding errors. Second, there is a conversation history, such as the previous 5 messages. This gives the LLM context about what the user has been talking about. And thirdly, there is decoding input, including noisy words and flags for low confidence tokens. This task of LLM is to recover the intended message with minimum changes. And this point is very important. The LLM should not creatively rewrite the user's message. It should preserve the user's intentions and only correct likely decoding errors. The goal is accuracy, not creativity. So, slide 10, correction and action. Here we have a simple example. The decoder outputs I read some water to tank. The decoder The sentence contains several corrupted words. Weed should be probably need. Water should be water. Pink should probably be drink. The LLM correction becomes I need some water to drink. In this example, the word error rate improves from 75% to 0%. Of course, this is a simple example, but it shows the main idea clearly. The BCI decoder gives a noisy approximation, and the LLM uses a language structure to reconstruct the intended sentence. This can make communication much more practical for users. Let's go for slide 11. Evaluation methodology. For evaluation, our approach uses a simulation-based method. We use 500 sentences from AAC literature. AAC means argumentative and alternative communication. These sentences reflect common communication patterns used by people who rely on assistive communication systems. The synthetic errors are injected into these sentences at different rates, so 20%, 35%, and 50%. The errors types are designed to match real BCI error disruptions, including substitutions, deletions, and insertions. We test three conditions. The first condition is corrected with no context. The second condition uses recent context. Sorry. And the third condition uses full context. This allows us to measure how much conversation history helps the LLM correct noisy BCI output. So in slide 12, expected performance gains, the expected result is a clear improvement in communication quality. The main metric is word error rate, and the expected reduction is around 30 to 40%. Another metric is semantic similarity using BERT-based evolution. The goal is to reach semantic similarity above 0.85 compared to around 0.60 for the baseline. This means that even if the exact words are not perfect, the corrected sentence should preserve the intended meaning. Another important metric is the overcorrection rate. This should be below 5%. Overcorrection happens when the LLM changes something that was already correct or changes the user's meaning, and this is a major safety concern. Latency is also important. The target is usually less than 2000 milliseconds using an API. For real communication, the system must be fast enough to feel usable. And for slide 13, ethical safeguards. Ethics are very important in this project because the system is dealing with a human communication. The first principle is user autonomy. The system should always show raw decoded text alongside the corrected version. This allows the user to understand what the system changed. Second, the system should require confirmation for low confidence corrections. If the LLM is not sure, it should not automatically decide for the user. It should make sure about the intended sentence. Third, overcorrection should be tracked as a primary safety metric. The LLM must not change the user's intention. Privacy is another concern. BCI communication can include a very sensitive personal information. In the future, on-device models may help protect user privacy by reducing the need to send data to external servers. Equity is also important. Many LLMs are stronger in English than in other languages. For real world deployment, multilingual support must be improved. So what's next? There are still several limitations. First, the current evolution is simulation based. This means the system needs to be very validating using real BCI hardware and real users. Second, performance may decrease when the input error rate becomes higher than 50%. If the decoded text is too corrupted, even the LLM may not have enough information to recover the intended message. Third, language and vocabulary limitations remain language and vocabulary limitations remain. Users may have personal ways of speaking, specific medical needs, or multilingual communication patterns. Future directions include fine-tuning language models, especially for BCI error correction. Another important direction is personalization, where the system learns from the user communication history. This could make the correction more accurate and more natural for each individual user. Slide 15, key takeaway. So to conclude, large language models can significantly improve brain-computer interface communication by correcting decoded error using knowledge of language structure. The mainstream of this approach is that it is modular. It does not require changing the entire BCI hardware system. Instead, it adds an intelligent correction layer after decoding. This can reduce errors, improve meaning, and make BCI communication more practical for people who depend on assistive communication technologies. At the same time, the system must be designed carefully. It should respect the user autonomy, protect privacy, and avoid changing the user's intended meaning. Overall, our project shows that combining BCI systems with large language models can create a more reliable and human-centered communication systems. Thank you so much for watching. I wish you have a good day.